changed. Okay, here is the time profile from inverse Fourier transform to time domain. Okay, so this is the last summary. We have demonstrated a negative group delay in an anisotropic waveguide system. This study provides a mean to control the group delay by simply change the polarization azimuth of the instant wave. So up to this point, we know the mechanism of superluminal effect, and we can control the group delay from positive to negative. Finally, I would like to conclude today's talk with several definitions. This is the simplest one, phase velocity. Okay. Phase velocity can be faster than the speed of light. Easily. No one worry about this phenomenon. Group delay is defined here. When group delay faster than the speed of light, we prefer another definition. That is when group velocity exceeds the speed limit, we prefer another definition. That's group delay. It can call apparent group velocity or just phase time because it associates with phase time. But not phase velocity, it's different. This one is probability velocity. Okay, in quantum mechanics. This one cannot exceed the speed of light. Energy velocity obviously cannot exceed the speed of light. So only these three, maybe just these two, maybe. With any other definition about a wave? Yes, about the phase, about the velocity. We have two more definitions. One is the information velocity. That is the speed at which information is transmitted through a particular media. The other one is signal velocity. Information velocity and signal velocity are closely related. The speed at which a wave carries information. These two obviously cannot exceed the speed of light. If these two exceed the speed of light, then we will have a big trouble. The biggest trouble is causality, 因果律. We will have big trouble. So this one greater than the speed of light doesn't matter. Okay, and this one group delay. This one less than the speed of light, less than the speed of light, less than the speed of light, less than the speed of light. And these two do not have a well-defined equation. So people try to define the information velocity and signal velocity. They always try to use a new definition about this one. Up to this point, we are using Gaussian wave. But if we want to study information velocity and signal velocity, then we have to use slightly different wave, rectangular wave, for example. Okay. This is the last figures, last one. I have 20 students, but only 5%, that is one student, work on these topics. Only one, this one. He has been studying these topics for about 7 years. When he is a junior student, undergraduate students. Right now, he's a PhD student, 4th year. Okay, so I would like to thank him because without him, we will go nowhere. This is not that easy because you have to develop the theory, you have to write the code, you have to perform the simulation, and conduct the experiment. So it's not that easy. So only one student work on these topics. It's not that easy. Okay, I would like to thank Professor Winford because Professor Winford gave us many precious comments on our research. concludes my talk. Thank you.
So it's very interesting talk, so that we know what is superluminal wave and everything about the propagation about this wave. Any questions?
Yeah, I have a question. Can you go to your conclusion? So you have energy velocity, you have Poynting flux by energy density. Now, but presumably when you can divide the Poynting flux into two parts. One is transmitted faster than the speed of light, and reflected. Can you?
In a single media, the result will be less than the speed of light. In a single media, even though we can see the full wave and then reflect the wave, yeah, there will be less than the speed of light.
I mean, I'm talking about your transmission pulse experiment. You have a fat waveguide and then thin waveguide, fat waveguide. Now, in this experiment, you have in the transmission part, you see the pulse out, and but there are still a lot of things reflected.
Yes.
So you can separate that into two parts.
Yes.
And so then, but the one reflected, transmitted, is really faster than the speed of light.
From this boundary to this boundary, yes, but in the middle, still less than the speed of light. Because of the boundary effect, so it looks like faster than the speed of light. In the middle, in the region of interest, still lower than the speed of light.
But you look at the delay, right? You compare the delay with the speed of light, or you have two parts, and one part is just the wave packet propagate, and the other part it goes through this device, and then you see the information, the pulse itself is when the pulse going through your device looks like travel faster than the one without going through your device.
Yeah.
Then it looks like this experiment shows faster than speed of light.
Yes, let me show you. This is a region of interest. We have first boundary, we have second boundary.
Right.
If the wave packet is very small, for example, like this one,
Right.
then it's impossible. This one will faster than the speed of light. It's impossible. The wave packet must be much larger than the size of this one. So the wave packet is much larger.
Right.
So I am the peak.
Right.
Part of the energy is into the cavity. So it bounces back and forth inside.
Right.
So when the peak into the cavity, okay, and then up to this point, the energy is built up because of bounce back and forth. So energy is built up, and just like cavity effect, some of the energy will leak it.
Right. But
So-
it still remain a pulse.
Yeah, remain the same shape.
Right.
It's distortionist. So when the peak coming out, the shape is saturated. So looks like it's ready to come out. So looks like no delay. Looks like. Yeah. So it's an interference effect plus model effect. 100% transmission is impossible.
Yeah, I understand. Yeah. You rely on the evanescence, so evanescence or something reflection inside this cavity. Yeah.
Yes.
I'm saying that because from your pulse experiment, it looks like the pulse, although it decreases in amplitude, but when it get out, it's faster than the one that without the free path.
Looks like. Yeah, looks like. But the amplitude is much smaller.
Yeah, I understand. But
We
still.
care about distortion piece. So this is a relatively broad band in this region. However, for slow wave, it's a narrow band. So that's why the wave packet is distorted.
Right.
Yeah, but in our case, just distorted a little bit here.
Oh,
Yeah,
only the effect is
a little bit.
it's not a peak.
Yeah, not a peak. The peak is almost the same. So this is the group delay definition. But if we come to the information velocity, we have to embed something here. In that case, there will be much smaller. They will be smaller than the speed of light in general.
Yeah, if you look at the peak, normally people compare the peak, not the foot.
Yeah. So maybe we should use something digital and control the group delay.
Yeah, it's an excellent intellectual exercise. That's already that's already good enough for a professor. But I'm sure you have something in mind in terms of application.
Yes. Yes. Okay. Actually, we can implement such an idea in a transmission line, such as microstrip and strip line. Actually, I have a student, which is a senior student. He studied this topic and fabricated such a device using a simple microstrip. And he can demonstrate such idea easily. And unfortunately, or fortunately for you, he will become your student. So my idea is we can control the junction, the boundary phenomena by using some kind of transistor or some kind of active device. Then we can control the group delay. By doing so, we can adjust the group delay, active control. It might have some application in communication. Active control. So this is very important. For example, in DRAM, they care about the group delay. So by doing so, we can control the group delay much easier. Although the transmission is low, but we can add an amplifier to boost the overall power again.
Any more questions? Okay, if not, let's thank Professor Zhang again for a very wonderful talk.